So hello everyone. So today we'll be getting into more complicated models. And if you recall from the past three sessions, what we have actually done, we have laid the foundation for understanding generative models. And in particular, we have studied variational models. We have done variational models, variational inference. This is recap. And in variational inference, what we have done, they have been including the EM algorithm. We have done GMMs. We've done VAEs, and we have done variants of VAEs. Right, so info VAE and beta VAE, and we have shown using code that they perform well at generation, at clustering, and at uh, categorization. So we can use them for clustering. We can use them for uh, what did you say? So you could use them for generation, and then you could also use them for reconstruction, various other purposes, and getting latent representations. So we have learned that when there are latent variable models, so variational inference models are based on latents, and these latents are sort of causal latents which explain the data. So if you change a set of idiosyncratic or features, for example, from a normal distribution or a uniform distribution, you have the control over them, and by changing those distributions, you could change the output of the variable. So we gave an example where the face could have five latent variables. One could represent the size of the nose, the skin texture, and size of the eyes, and whether they're smiling or not, and the skin color and the hair color. And each of them could be like sliders, which you have access over. Maybe a uniform distribution, you could just slide over 0, 1, and then you could change the face structure. So because data is often told to be existing in a low dimensional manifold. So these are what we have discussed from the last time. And today, what I'll do is we'll be continuing with variational inference models. So VAEs have been known to do likelihood estimation, generation, and clustering to be they're fairly efficient at doing such things. So today, what we'll be doing is we'll be going one step beyond the VAEs and go towards the state of the art image generation model. So if you go and put a prompt on ChatGPT today or Gemini today, at the back end, they would be calling what is called stable diffusion. The stable diffusion model is what is going to generate the image for you. And once you generate the image, that is what the chatbot will give you. So any image generation or video generation has this sort of a diffusion model involved in it. So you could have variants of it, but the general idea is of a diffusion model. So you could think of a diffusion model as a hierarchical VAE, so or a multi-step VAE. What do I mean by that? So we know that there is this encoder in a VAE. So you give X and you get Z from the encoder. And you could say that I'm going to have multiple encoders. I'll have E1 as one encoder, and then I will pass the latents. And sometimes what you do is you add mutual information as you do in an info VA so that the maximum information is gathered through the latent. So you have a contiguous flow of latents of information through the latents. But we'll not go into the details of that. It's not really relevant for this. So what we can say is that we get the latent Z1 and we further want to compress it to Z2 using another encoder. So we could do the same process over and over again using a VAE, and then you could have a decoder that decodes from D2, and then you could have this structure of which decodes D1. And then this is often called as a hierarchical VAE. So where what you do is you have a latent Z1, and that latent often explains another set of latent Z2, and that latent explains the data. So you could have this flow of uh, date flow of structure in the code. So for example, you could see that the latent Z1, which could be very small dimensional, and it could have fine details, and you could add another set of latents, which is and it could be transferred. It could explain another set of latent Z2, and that could explain the data finally. And you could have multiple other factors. So each of these, for example, could have another variable Y, for example, which could represent the category of the data. For example, often in VAEs, people do that. Say the first latent is independent of the class of the data, and then the second variable could, you could say that given the first variable and the class, you're going to generate a latent, which eventually is going to generate the data. So these sort of things are often done in a hierarchical VAE. So here, what does it mean? That Z2 is explained by a set of latent Z1 and say the class of the data. And class is in your hand. So you could say 0 for cats, 1 for dogs, and Z could represent the texture of the hair of the dog and things like that. So for each of them you could have control over, and one of them could actually have a meaning. For example, class is actually a variable which would, you could exactly know what 0, 1, 2 and things like that could mean. But that's a story for another day. So the idea here is to have this flow of latents. So multiple latents arranged hierarchically to explain the data. Often for better reconstruction or interpretability. So here you can see that the X and the Z and the Y, the latents that explain the textual, the features of the data X, and the Y, which represent the class category, are sort of separated out. So you could have better representation of better understanding of the latents. For example, the same set of latents for a dog could indicate the color of uh, the the color of the hair of the dog, and could also represent the color of the hair of cat. But you could just change the level Y, and you could have the cat converted to a dog. So interpretability as well as reconstruction are often the reasons for having this multiple hierarchical structure. So they're often shown to be working better. So you could see this hierarchical VAs being used as encoders in diffusion models. We'll go into that in the future, and we'll see that these are better than just having a one layer VAE. So, but today we'll be doing what is more important and what is the state of the art is we'll try to extend this idea of hierarchical VAE to this idea of a general purpose, a diffusion model. So in diffusion model, what happens is the overall idea, as you can think of, is you can get through this image that I have over here. So we'll not go into what these specific terms mean, but if you can look at the image here, on the left-hand side, these are natural images. And these are noise vectors. And what I see is that I am doing a process, forward process Q, in which I'm going to add noise. So what I'm doing from here to here is at every step is adding noise. And I add noise in small amounts, small quantities. And until I reach a noise distribution. Right? A noise distribution is a normal 0-1 distribution, which is very easy to sample from. We all know how to sample from it. We have callers, libraries that call the normal 0-1 distribution and so on. So that's said and done. So what we'll be doing is, given natural images, we'll just add small amounts of noise. So a diffusion model, all it does is it adds small amount of noise to give you a completely noisy estimate. So why do I need a completely noisy version of the data, which is from a normal 0-1 distribution? Is because when you're doing inference, just like a VAE where we regularize it to be near normal 0-1, I will sample Z from normal 0-1, and then I will denoise the data. And I'll get the get a novel image. So that's the idea. So the idea is I'm going to add small amounts of noise and I will learn what noise was being added at every step so that when I finally sample from a noisy distribution, when I'm doing the denoising, I can get novel images and we'll see what that means. What does that mean? And it can be thought of as a Markov chain. So the goal is, as I have mentioned, is being able to sample from this normal 0, 1 distribution. And then finally, you keep adding noise, and then you get this noisy distribution. And what you end up doing is you learn. So this process is sort of it is a deterministic process. Deterministic, it is stochastic process, but it's a Markov chain. The forward process, if I write it down, forward process is a fixed Markov chain. Markov chain, and nothing is learned. What do I mean by that? I'll come to it. But we, in the reverse process, what we end up doing is we learn the opposite of the forward process. Of the forward process. That is denoising. So these models are often called denoising probabilistic diffusion models, or DDPM, diffusion denoising probabilistic models. And these were one of the first papers in the field of diffusion models. This is by Ho et al. In 2021, 22, maybe. And then just caught the field by storm, and it made GANs, which we'll be studying next, invalidated and things like that. So what we are going to see is we're going to see how we are going to do this forward process and what does this reverse process mean. So we have seen that we have this image. I'm going to add noise. I'll get a noisy image. And I will learn the reverse process of removing the noise. Right? So what I mean, what is this model all about? Why is it called a diffusion model? It is called a diffusion model because if it follows what is the diffusion equation or the diffusion process. In a diffusion process, what do you know? You add something in a low concentration, in a high concentration region. This high concentration region, the particles in the high concentration region normally flows towards what is known as low concentration. Why does that happen? Because anything that has low entropy in the world will try to go towards more randomness and more entropy. So as you disperse the models, the particles are going to go to complete randomness or maximum entropy. And similarly here as well, we're going to add. So images, as we have shown, are zero probability sets. So natural images are. And what we are doing by adding noises, we are taking these images towards a completely random normal 0, 1 distribution, and which is like completely random noise and has maximum entropy. There's no interpretability of random noise or white noise. So when you go towards normal 0, 1, we're actually doing this is actually doing a diffusion process of increasing randomness. And we see that finally we get complete randomness, right? Normal 0, 1 is as random as you can get. These are all possible combinations of the pixel values with definitely a PDF associated with it. So yeah, we get a completely random image. Now, as we get a random image, we will see that we will learn to denoise that image somehow. So I'll slowly remove this noise. And you may ask me, why not add a very, very high amount of noise? So the people often ask, why not add huge amount of noise? Just do it in one step. That is, just convert to normal 0, 1 in one step. The answer is only when the amounts of noise added are small, are each of the steps reversible. So you can think of this as an adiabatic process, which is reversible, which means that every point when you add a little amount of noise, you could reverse that process. But if you add lots of noise, there's no way you could recover that noise back. So only when there's small amounts of noise is added at each step can each step be reversible. It's a thermodynamic interpretation of diffusion model where each step only becomes Markovian, or the reverse process only becomes Markovian. The idea is that if you want to put it down mathematically, the reverse process becomes Markovian or reversible only if there are small amounts of noise that is infinitesimally small over infinite steps. If there are only small amounts of noise added over to get the noisy image, right? So only then can your reverse process be defined. We'll see what, and all of this will make sense, but this is good to keep in mind that why do I need to add this in small amounts? It's like one particle just moves a small amount, only then can I say just reverse it back. And exactly, then only can I put that particle back into action, because the particle in a random diffusion moves in all directions. And if the particle ends up somewhere here, that it could have gone in infinite trajectories, and each of these trajectories could be very, very difficult to trace back. So it's not reversible. So it's impossible to trace back a particular trajectory it went by. But if it just take an infinitesimally small path, so you exactly know which vector, you could just approximate by it a line through between those 2 points in this particle. So that's the reason why we take it to be the noise to be extremely small, because you can think of this as this trajectory. So if these 2 particles are somewhere here, particle at T1 and T2, if T1 minus T2 is large, or T2 minus T1 is large, so you could have infinite paths between these. You could think of in diffusion, you could have this path, you could have this path, you could have this path, and when I'm trying to denoise, I have to take the exact path which it went by. This is the denoising. Denoising is impossible if the distance between noisy states is large. Instead, if these T1 and T2 are very small, you could just take a linear approximation between T1 and T2 by using calculus, if delta T tends to 0. So this is the entire idea you should keep in mind when we are doing this denoising diffusion model. And so this is akin to large amounts of noise. This is small amounts of noise. So this is reversible. I can exactly go back the same path. It's like an instance stick. If I had tracked each particle at each point in time, then I would take every step of that particle and get back the instance stick in the corner of a room. So it's like in a forward process in a diffusion for an instance stick is like you put an instance stick at a corner of a room and the particles are uniformly distributed throughout the room. And you exactly do not know which particle was from which part of the instance stick, but if you've tracked every point on the trajectory, so you could reverse each of the point in the trajectory and get back from the isotropic room back to the instance stick at the corner of the room. So that's the idea. So now let's look at the mathematically, what does it mean? So mathematically, I'll show you the image first and then we'll draw it anyways. So it's like So here I'll be using, so Zs have often been used for notation for latents, but we'll be using the notation of x1 for z1, x2 for z2, and xt for zt, and x0 for data. So what I'm going to say is I'll be taking the data x0 and I'll keep adding noise. So this is the first noise 1, this is noise 2, and this is noise t. And corresponding to each of the noise, I will learn denoising t, denoising 2, denoising 1. And this is all it is. You can see it's clearly like a hierarchical VAE where we are encoding. This is encoder 1, encoder 2, encoder t, where the forward process is not learned, but the reverse process is the decoder, decoder 1, decoder 2, decoder t, which is going to be learned eventually. So let's look at it. How are we going to define and how are we going to learn? How is the noise going to be added? So let's look at the forward process. Don't look at the left for the time being. Look at the right. So we'll define the forward process. Let me just note it down if everything has been. So the idea has been cleared, and we have learned what is the what the overall goal of the model is. Now let us look at how we will get to the forward process. So the forward process is what I'll define now. Say Q. So we will define this as x0 is the image, and we have a set of latents, which I'll be putting in this box for the time being for you to note down well. So this is x1, x2, and I'll go on till xt, where t tends to infinity. But in real, you cannot make t to infinity. You take it to 1000, 2000, and so on. 500 are generally the steps that we generally take in a diffusion model. So you see that from the x0, you move to x1 by adding, say, a noise epsilon1 from a normal 0-1 distribution. But how do I combine it? And then similarly, from x1 to x2, I will add again another noise, which is again sampled from normal 0-1. So you can see that the forward process between xt and xt plus 1, or you can say xt minus 1 to xt, for all t is a Markov chain. So what does it mean? That xt only depends on xt minus 1. That's what it means. So let's look at this. So you can clearly see I'm going to add this noise, and I told you this noise must be added in small amounts, which means xt is what I'll be defining as the tth latents. These are the latents x1 all the way to t, and data is x0. So xt will be xt minus 1. So I will have the original image and I will add a small amount of noise. So how will I do that? I'll do that by weighing it with alpha t, where alpha t is tending to 1, say 0.99 example, 0.999, and I'll add a small amount of noise. How do I do that? 1 minus alpha t into epsilon, which is sampled from normal 0-1. Right? So what does it mean? Now you can clearly see, you can tell me if you take the expected value of xt, right? What will you get? You'll get this is normal 0-1. So this is expected value of root alpha t xt minus 1 plus, and I'm telling that xt minus 1 is given to me. So this is a conditional distribution plus the alpha t. This is given xt minus 1 epsilon into this constant. Right, so this is 0 because it's come from normal 0-1 distribution. The expected value of normal 0-1 distribution is 0, and this is equal to, and this is given to me, both are constants. So I can just say this is alpha t xt minus 1, right? Similarly, given the variance of the data, so this is the mean of the data. So what is the variance of the data? Or the covariance matrix can be defined as xt minus expected value of xt into xt minus expected value of xt transpose given xt minus 1. This is what we are going to define as the covariance given the xt minus 1 variable. And you can clearly see that this part of the data. So you get the means removed. So this is the mean, which is already there in the equation. So xt minus expected value of xt will only have this part, which is the expected value of 1 minus alpha t epsilon into 1 minus epsilon or 1 minus alpha t epsilon transpose given xt minus 1, which is now independent. So you get 1 minus alpha t and expected value of epsilon's transpose, and we know that they are independent of one another. So sorry, they are this epsilon, the expected value of epsilon, which is already sampled from normal 0, 1. So we already know the variance of epsilon, and therefore this is equal to the identity matrix. So we will get 1 minus alpha t into I. And you can look at it in a different way as well. So if each of these distributions are assumed to be from a normal distribution, so xt minus 1 is normal, so xt plus xt is normal, and given xt, all of these are going to be normal. So which means we can clearly see that q of xt given xt minus 1 is distributed. So xt minus 1 is given to me, and since epsilon is from a normal distribution, so this is like mu plus sigma t. So this is mu, and this is sigma, and this is epsilon. So mu plus sigma epsilon is known to be sampled from a distribution of mu and sigma square, right? Sigma square I, we know that. So we know that x is equal to mu plus sigma z, where z is sampled from normal 0, 1, means x is sampled from normal mu sigma. That's what I just showed you just now, mu sigma square by transformation of random variables. We know, right? So we can write this as normal distribution of xt root alpha t xt minus 1 and 1 minus alpha t into the identity matrix, right? So where alpha t tends to 1. Right. So now I know exactly the forward process. I know exactly this is a normal distribution. Every point I will be able to. So this is how to get tth noisy image from t minus 1. But you can see there's a problem. And if you have identified the problem with this forward process, the problem is that xt minus 1, if you have to compute xt, you will have to go through all the points, xt minus 1, xt minus 2, and all the way to x0. And this is very cumbersome, computationally expensive. So the idea is, can we directly get tth noisy image from data x0? So this is the idea that I have, right? So can I directly get the tth noisy image from the data x0? So I know the process from xt minus 1 to xt, then I'll do the same process. Can I do induction and get the value from x0? So I know that xt is equal to root alpha t xt minus 1 plus 1 minus alpha t epsilon. Let's put epsilon t for the time being, and every epsilon t are sampled from normal 0, 1, right? So now we know xt minus 1, I can use induction in the same manner, and I can expand it as root alpha t minus 1 xt minus 2 plus 1 minus alpha t minus 1 x epsilon t minus 1, right? Plus 1 minus alpha t epsilon t. So this is what I can write this as in terms of xt minus 2. And this will become, so you can say this is equal to alpha t minus 1, right? xt minus 2 plus alpha t minus 1 alpha t into epsilon t minus 1 plus root 1 minus epsilon t alpha t epsilon t. So now you see clearly you have a mean and you have a sum of normal 1 and normal 2 distributions, right? So there are two normal distributions and you have a constant. So what is this distribution? So we know that sum of two normals independent IID is normal mu1 plus mu2 and sigma 1 square plus sigma 2 square. We have studied this in probability. So if you have independent normals, sorry, not IID, independent normals, and here it is IID as well. No, sorry, because we have different scaling factors. The epsilons are IID, but the multiplication factors are not. So it is like having sum of means and sum of variances, right? So sum of means here are, you can clearly see expected value of mu1 is equal to 0, expected value of mu2 n2 is equal to 0, because both epsilon t and epsilon t minus 1 are normally normal 0, 1 distributed. Similarly, the sigmas are, we know, the variance of normal 1 is equal to the covariance matrix of normal 1 is alpha t minus alpha t minus 1 alpha t, right, into the identity matrix. The covariance matrix of normal 2 is 1 minus alpha t, the identity matrix, right? So we can clearly, because this is just the multiplication factor, and we saw that if this is sigma 1, this is sigma 2, this is just the square of the sigmas, right? We have shown this just now, which means that if I add these two, I will get normal 0, and I will get alpha t minus 1 alpha t minus plus 1 minus alpha t, the identity matrix, which is distributed as normal 0, 1 minus alpha t minus 1 alpha t, right? And I have this constant term in front, this constant term, right? If I have this constant term in front, so if you could put this with any of the normals, and you could say that, or you could say that it's just a constant that is added, so they could just add the expected value to both the normals. So you could say that q of xt given xt minus 2 is a constant. This is normal 0. Again, you can write this as normal, where variance is 0, because it is a constant value, and the mean is alpha t minus 1 x2 minus xt minus 2. So again, it's a sum of all the means and the variances. 0 plus 0 is this variance, and this is the other variance. So this is n constant. So you get xt minus 1, xt minus 2, and so on. So you will get normal xt alpha t minus 1, xt minus 2, and 1 minus alpha t minus 1 identity, right? So now you can clearly see that I got this value for 2 as well. Similarly, by induction, so if I keep going to qt given x0, which is the image, or what is the data, we can say that this can be written as xt, and you can clearly see by induction, this is the product of t equal to 1 to small t alpha t x0 into 1 minus product of t equal to 1 to capital small t alpha t identity matrix, right? So this is what I'll get. So now I will be writing this as, from now, the product of the alphas as alpha bar. So given the data, I can write this as alpha bar x0, 1 minus alpha 0 for alpha bar identity. So this is my, given the data, what is the distribution? So clearly now I can get the tth rand noisy version of the image directly. So we have been able to find this distribution. We have shown this encoding is a forward process, which is deterministic. Deterministically, which is not learned. It is not deterministic, it's a Markov chain stochastic. By deterministic, whenever if I say the forward process is deterministic, it means that I have predetermined process of generating the latents one over the other. It's not by an encoder. It's what I mean. A neural network is not going to give me that value, is what I'm trying to explain. Okay. So now we have seen this term. So I have been able to write down. So I'll write it down over here. So the forward process so have a schedule alpha t, t from t belongs to 0, 1, 2, dot, 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 capital T. Sorry. So this is my schedule. This is called a schedule of the noise mixer. So how much amount of noise am I going to add where alpha t's are close to 0? So I will know that the forward process xt given xt minus 1 is a Markov chain and is normally distributed as mu alpha t xt minus 1 and 1 minus alpha t identity matrix. Because it does not have any covariance. Each of the latents are assumed to be independent of one another. Similarly, xt minus xt given xt x0, which is my direct t-step process. So remember that my direct t-step process is this forward process is I'm getting the value directly, but actually we are actually doing an encoded t-step of adding small amounts of noise. It's not like that I'm adding a huge amount of noise to get the tth noisy image. All this is encapsulated in a single distribution because I have been able to show that it is normally distributed because of the linear property of mixing, right? So I get xt and I get x alpha t bar, x0, 1 minus alpha t bar identity. So alpha t bar is the product of t equal to 0 to 1 to t. Now alpha t's have to be, so as t tends to infinity, what do you get? Product of, or capital T tends to infinity, t equal to 0 to capital T, alpha t will go to 0, limit t tends to infinity. Can anyone tell me why? This is because product of infinite less than 1 terms is equal to 0, right? So you're multiplying very terms less than 0. So we're going less than 1. So if you keep multiplying infinite of them, it is going to go to 0. And we're going to schedule it in that manner. So which is 1 minus epsilon to the power infinity will give me 0. That's the idea. So I will have terms which is finite and it will be lesser than 1. And I'll have infinite of them. And if you have infinite less than 1 terms, they're going to be that product would get to 0. Therefore, 1 minus alpha t limit t tends to 0 goes to 1. So therefore, q of xt given x0 limit t tends to infinity goes to normal x capital T 0, 1. Right? So what do I see? That indeed, yes, the forward process slowly is able to convert any image or data to normal 0, 1 or isotropic noise. Right? So now with that, we have understood what the forward process is, which is just an addition of the noise. So if you see, it is just xt minus 1 root alpha t. So when you write a mu sigma distribution, you know that it's mu plus sigma z. Sorry, it's not sigma, it's alpha here. And that becomes your random variables, transformation of random variables. This is mu. This is mu. And this is your sigma. So mu plus sigma z is how you transfer, as I've shown you over here, between normal 0, 1 to many mu sigma squared distribution. We have seen this in details in our previous courses of statistics. Anyways, Here Z is the epsilon, which is normal 0, 1, if you're just confused by what I was saying. Okay, so now I know what is qt given x0. Now I'll be trying to see what is we have shown that adding small amounts of noise makes the reverse process Markovian. We have understood the intuition because each of this process can be approximated by a linear sum, which is not possible by this huge non-linearity present, non-linear paths present, infinite non-linear paths present between T1 and T2 when the time points between the two processes is large. So we want infinite time points so that I can track every small noise additions. So I want infinite time points and very, very small distances traveled at every point so that each step becomes reversible. That's the idea. We have understood that each of the step now is linear, and whenever the reverse process is linear, it also becomes Markovian. So this is not Markovian, but this is linear, and hence only depends on previous state. So it's Markovian again. Not Markovian, not Markovian as in reverse process is not Markovian. And here reverse process is Markovian. Right? So let us try and write down the distributions of joint distributions of the encoder and the decoder. That will help us. So the joint distributions. Right? So joint distributions I have shown as x0. This is q, x1 given x0, x1 and all the way to xt, q of xt given xt minus 1. Right? And the reverse process is p theta is what we're going to learn, decoder. P theta of xt minus 1 given xt. And so on. And I'll get p0 of given x1. Right? This is all the reverse process. Whatever I'm doing in the forward process, reverse process, since noise added was small, reverse process is Markovian. So it means that only xt minus 1 depends on xt. So let's look at the joint distributions. So a joint distribution of x0 to capital T. Again, since it's due to the Markovian property, given the previous state, it's independent of all previous states. You can clearly see that from the graph structure as well. So this will be, you can write this as q of xt given x0 to t minus 1 into q of x0 to t minus 1. So once, as soon as this is just by law of total probability, not this again by Bayes rule, as you can write this conditional distributions, rule of conditional distributions. And then I just factored out xt, the tth variable, and conditioned on every other variable. As soon as I do that, by Markovian property, I can write this as q of xt given xt minus 1 into independent of x0 to t minus 2 given xt minus 1 into q of x0 to t minus 1. Now again, by induction, this can be factored as q of xt given xt minus 1. Q of xt minus 1 is the last state, xt minus 2 into q of x0 to t minus 2. So I used this factorization again in this factorization. Right? So and this by induction can be gone all the way to pi of x t given xt minus 1 t equal to 1 to capital T. Right? This is what I'll get. And I'll also have a, I think, a q0 term, x0 term. Right? Because in the last term you will have q of x0, and I'll go all the way down. I'll get x0 and x1, which can be written as q of x1 given x0 into q of x0. Right? So it's a joint, so I can write this as q of the latents. the latent distributions joined given the data is, so this is Q of x0 to xt, and I'm taking it on this side, and by conditional probability, I can write this as t equal to 1 to capital T, the product of the individual normal distributions, right? Remember, these are all normally distributed. So as long as they're normally distributed, we're all good, because the products of normals, your factors of three normals, they're generally normally distributed. They add a sum of normals, they're also normal. The products of normals, they're also normals. So that way we're good to go, as long as we have them to be normally distributed. So let us find out what the next one is. So I think the product may not be normal. I think the product by a normal is going to be a normal. So AB by B is a normal. So we'll see that. So, okay. Product mu1 into mu2 into the power of 22. Correct. So let's now try to understand what we're going to do after we have found out the joint distribution, we'll have to have a look. We'll have to have a look at the decoder distributions, right? So each of this forward process are normally distributed. Now, what about the reverse process? The reverse process I've assumed is to be normally distributed. That is xt or x0 given x1 all the way to xt, p theta is p0 p theta of x0 given x1, since reverse process is Markovian. Okay. So it's saying that given a future state, the previous state is only dependent on the future state, because the future state was a small timestamp ahead of the previous state. So you could just reverse it. So in the same way, p theta of x0 to t can be written as p theta of, again, x0 to x1 to t by law of conditional probability, x1 to t. So this becomes p theta of x0, x1 into p theta of x1 to t. This becomes equal to, again, I can write this by induction as x1 given x2 into p theta of x2 to t. I keep doing this, I'll be getting this as p theta of xt into the product of t equal to 1 to capital T, p theta of x0 or xt minus 1, xt minus 1 given xt, right? This is what I'll get. Okay. So once I get that, so I know the two joint distributions, p theta of x0 to t, and I know q of x1 to t given x0. These are two joint distributions I know, and I have been able to factor them down. Again, factored out by a set of normals. Okay. So this is also an assumption. We will see the details of this assumption now. How are we going to do it? So now I completely have the joint distribution of x0 to t and a p theta of x0 to t, and I have the complete joint distribution of the encoder. This is the encoder process for the variational distribution, where I'm making the encodings, and this is the decoder distribution, decoding process. So, okay, so now if I write down the ELBO, so this is also we have written this down. We've been able to write down, factorize the joint distribution. And so now let us write down the ELBO. So we'll write down the ELBO. 1 second. Yeah, we'll write down the ELBO. and we'll try to see what we can factor out the ELBO as. So the ELBO is going to be complicated. So for ELBO, we know the ELBO can be written as. So let us represent this as by f theta, because it does not have an encoding process. We're not going to learn it. It is predetermined by a set of Gauss normally distribution noise additions. So we know that the ELBO is often defined as QZ, where Z is the latent given X. We have defined this in the previous lectures, and this is a joint distribution of the data and the latent under the model, under the decoder model, by the variational distribution, right? The Q of Z given X. So as soon as I write this, you'll be able to tell me what are the Zs here. Zs are x1 to t, Zs are x1 to t, and this is x is equal to x0, right? So as soon as I do that, I'll be able to write down the ELBO f diffusion model as expected value of Q of Z given X log of p theta of x0 to t, Q of x1 to t given x0, right? This is my ELBO. And as soon as I write this, you can see I have already defined. I'll put a star and a dagger. This is my star. I know the star already being defined. And this is my dagger already defined. So I can just put these values and I can factorize, because each of these terms will be factorized out and I'll get a clean set of individual terms, right? Let us get the clean set of individual terms. So now you can see I can write this as the expected value of putting star and dagger, right? If I put star and dagger, I'll get Q of Z given X, the log of the product of t equal to 1 to capital T, p theta of xt minus 1 given xt into p theta of capital T. We know this is normally distributed, normal 0, 1, right? Because we're going to sample from the normal 0, 1. This is the assumption that we have, that the marginal distribution at the end of the time would going to be normally distributed. Okay, once I do that, the denominator also is a product, as we have written from the dagger term, is between t equal to 1 to capital T, Q of xt given xt minus 1. Right? This is what I'll get. So now, to train the model, I have to sort of, the idea is to train this model, to train it, p theta must be closely similar to Q of xt given xt minus 1. But this is xt minus 1 given xt. So you can see that one p theta is trying to learn the reverse process where it gets the xt distribution, the future step, and tries to learn the previous step. But Q is trying to get the future step given the past step. So now the problem is I don't really want that. I want p theta xt minus 1 given xt to model Q of xt minus 1 given xt. So I want to model the posterior of under the variational distribution, because when those are similar, can I make an inference about, can I make a claim that the reverse process would be similar, right? So let us try to do that. So because this is the reverse process under the latent generation. And we wanted to learn the reverse process. So therefore, we will try to learn the reverse process directly. So let's try to learn it now. Now, how will I learn that? So let us try to write down. So by Bayes rule, what I can do is, first, there are two tricks over here. Q of xt given xt minus 1. You can write this as, would you agree to me, by Markov property, I can write this as xt given xt minus 1, comma x0, right? Now I can write this as these two terms. 1 second. So what we can do is we can write this in terms of, because it given xt minus 1, it does not depend on x0. So we can write this as xt given xt minus 1 and x0. Why am I going to put this? Because I want to have a control. I'm putting this x0 because I want a control over which image in training distribution I am using. This is the entire idea that I want to introduce this x0 term and see what happens. So these two are equivalent anyways, right? Once these are equivalent, I can write this as my base rule. So what I want again, remember I want the previous step given xt, right? So I can write this as xt minus 1 given xt and x0, right? So when you condition something, you're just taking xt here and xt here. So you'll be using base rule. You're conditioning on the reverse. The posterior becomes q of xt given x0 by q of xt minus 1 given x0. So this is a trick when you have multiple conditioning variable and you are trying to replace or use base rule on two conditional variables. You actually use the ones that remain fixed as conditioning for the rest as well. So normally P of A given B is P of B given A into P of A by P of B. So if you have another term C, that C gets conditioned on each of the other terms as well. So that's the trick to remember if you have multiple conditioning variables. So anyways, you could write down the joint and also factor it out. It doesn't really matter. So now what I'll do is, so I have this term. So I will write this product now. So let us write this product. So now I have got what I wanted. I wanted xt minus 1 given x0. So let us write this down. So I'll note this down over here. Xt minus 1. And then what I can do is I can write this as the product of q of xt given xt minus 1 t equal to 1 to capital T as the product of, or I'll write a few terms for you. X, say the first term x0 given xt or x1 given x0 into q of x1 given x0. This is the first term corresponding to t equal to 1, x0 given x0 into x1 given x2 given x0 by q of into q of x2 given x0 by x1 given x0, right? So this is all the terms will keep going on forever. So this is, you can clearly see this term is goes to 1. These two terms are same because q of x0 given x0 will just cancel out. These two terms will cancel out because once x0 is given, you don't need x1 to determine x0. Similarly, you can cancel out this term and this term. Similarly, all these future terms in the denominator will be cancelled out. So all you will be remaining is the last term. So the product of these terms, xt given xt minus or xt minus 1 given xt and x0, these terms would all remain because they're not going to be cancelled out from t equal to 2 to capital T. And what is the last term that you're going to be remaining left with? You're going to be left with, see this again. So you have this set of terms, right? These factors, these ratios. Sorry, you have set up these ratios. So if you write this down, q of x1 given x0, q of x0 given x0 into q of x2 given x0, q of x1 given x0, q of x3 given x0, q of x2 given x0, and so on. So these terms you can see clearly gets cancelled out, right? So when these terms get cancelled out, only what remains is q of xt given x0 because the last term is only will not have a factor. So I can write this as q of xt given x0, which is definitely again a normal distribution, q of xt, which is again normally distributed. right? We have shown that as t goes to infinity. And this process does not depend on any of learning mechanisms. So again, I can write down the ELBO as f theta as the expected value of q of x1 all the way to t x0 log of, I can write it as a product of t equal to 2 to capital T p theta of xt minus 1 given xt by probability of q of xt minus 1 xt comma x0, right? So what am I doing? Remember, again, if you're not following, so all I did was I factored this term. I'll put a double star. I'll put a double star over here. And I'm just putting the double star back into the equation. So I put the double star back into the equation and I will have one term here remaining, p theta of x0 given x1, right? And I will have q. So this is the log term. I have q of xt given x0 and I have p theta of xt, right? So I will assume that these two terms will cancel out because both are normal 0, 1. And even if they are not, these do not have parameters to learn from. The numerator is assumed to be normal 0, 1. The denominator, even if it is not, it does not have a parameter to learn from, so you don't have to worry about them. Ideally, they should both be normal 0, 1 as we have shown in the session today, right? So let's now try to see how I can factor them out. So now we have almost reached the end of the DDPM derivation. So now my factored out term, you can clearly write this as f theta can be written as the expected value of qx1 to t x0. I'm going to put this term out, log of p theta of x0 given x1, and I will have a summation of a negative. I'm putting a negative, we'll see why, of expected value of q of x1 to t given x0 log of q of xt minus 1 given xt comma x0 by p theta of xt minus 1 given xt. Okay. And this is a summation of t equal to 2 to capital T. Okay. So this is what I have. So I have a product. Log of product is a product of logs, the sum of logs. So I just wrote it as a sum of the individual terms. Why am I writing as a sum? Because each of these terms are symmetric. So computing one term computes the rest. Okay, the computing one term computes the rest as well. So therefore, I'm writing it as a summation of these individual terms. So now I can write these as, you can clearly see the first term can be written as an integral. So let us write these down in terms of the integrals. So this integral is x1 to t log of p theta of x0 given x1 t of x1 to t. So all you can see is this distribution on this that we have here only depends on x0 and x1. So right, so only depends on x0 and x1. I forgot to write down the q of x1 to t x0 d of x1 to t. So if I only depends on x0 and x1, so what I can do is I can marginalize out 2 to t. So I will marginalize out 2 to t x2 to t, and I'll get the expected value of x1 given x0 log of p theta of x0 given x1. So this is exactly what happens in a VAE, right? In a VAE as well, it's the reconstruction term exactly like a VAE. So you pass x0, encoder, get x1, and the decoder, you use a decoder, right? So this term is fine. So now let us look at the second term of this equation. The second term of this equation is this summation over the log, right? So what we can do is we can look at one of the terms. Let us look at term t from let's put what do we put from star 3, right? Let's look at term t from star 3. We'll be able to see that term, and what will we get? So look at this, the expected value of q of x1 to t given x0, the log of q of xt minus 1 given xt given comma x0, and p theta of xt minus 1 given xt. So what I can say is this term can be written as the integral of q of x1 to t x0 log of q of xt minus 1 given xt comma x0 p theta of xt minus 1 given xt, all the d of from 1 to t, right? So now you can see the inner integral only depends on xt minus 1, xt, and x0, right? So what I can do is I can marginalize out everything except xt and xt minus 1. If I do that, I can write this as marginalize q all x's except t comma t minus 1. So you'll get the integral over xt comma xt minus 1 x0. This is all between 1 to t. That means you have t integrals like this, and you're marginalizing t minus 2 integrals already over here because only 2 terms are there in the inner integral. So I can write this as log of q of xt minus 1 xt comma x0 p theta of xt minus 1 given xt, right? And you have d of 1 comma t, right? So now this term can be written as, again, by conditional probability, q of xt minus 1 given xt comma x0. This is an integral over xt minus 1. And I can write this as q of xt given x0 integral over xt log of q of xt minus 1 given xt comma x0 by p theta of xt minus 1 given xt. This is all. I broke this down into two p of AB into p of A given B into PV. That's all I did. So this is t of xt minus 1 into t of xt. So if I write this down, you can clearly see this is the KL divergence. Q log Q by P is the KL divergence between Q and P. So I will write this down as the DKL Q of xt minus 1 given xt comma x0 and p theta of xt minus 1 xt, and you have an expected value over q of xt given x0. Okay, so now combining all the terms, combining all terms, the loss function becomes, what does the loss function become? The loss function becomes very simple. So we will have this term and we have a sum of these terms, right? So that F diffusion over theta is the expected value of q of x1 given x0 log of p theta of x0 given x1 minus the expected value of q of xt given x0 T equal to 2 to capital T, dkl of q of xt minus 1 given xt comma x0 with p theta of xt minus 1 comma xt given xt. So what you're actually doing is, you can see the interpretation is we are trying to matching q of xt minus 1 given xt comma x0 with p theta of xt minus 1 given xt. Right, this is what we are doing. We're maximizing we are trying to maximize the ELBO. So we are trying to minimize this. So if you are trying to minimize this term, or minimize the KL divergence because it's a negative term. So what we are going to do is we are making the reverse process. We are learning, we are matching them, and hence learning a decoder that closely follows the posterior of the variational distribution. Right? This is what we are trying to do. So if I'm able to match that posterior at every step, so it's like xt minus 1 and xt, and this is giving me the q, and this p theta distribution is going to match the q of xt minus 1 given xt and x0. So once we are able to do that, we'll be able to do efficient denoising. That's the idea, right? So because we're exactly learning the reverse of the variational process which encodes, because we are learning the exact reverse of the variational process, variational encoding process. Okay, so now I have been able to get the loss function, but once I've been able to get the loss function, I hope that q of xt minus 1 given xt and x0 is a normal distribution. If it is a normal distribution, we have already found out. We already know this normal distribution. We will assume this to be normally distributed. We'll see what happens. Let's see what are the distributions. Okay, we need to know the KL divergence of each of this term, and hence, and we'll try to find out the terms distributions, right? That's the next step we'll do. It's very simple. So let us try and do that. So this term over here that we have is, we can write this as q of xt minus 1 given xt comma x0. We have written this as into q of xt given x0 by q of xt minus 1 given x0. We remember this was the factorization we had done here, right? This is the factorization we had done. So all I'm doing is I'm taking this on the other side, right? This is equal to q of xt given xt minus 1, right? Very good. So we can write this as, so if I take this term out, I can write that q of xt minus 1 given xt comma x0 is q of xt given xt minus 1 into q of xt minus 1 given x0 by q of, this is just algebra. And once you're able to be comfortable with it, everything falls into place. This was done for the factorization, right? Was done for the factorization purposes. And now, okay, so I get this. So now if you ask me, I already know the distribution of all these three. This, and this, all the three distributions are Gaussian. And if they are Gaussian, if you have A, B by B, then the product by a Gaussian is also defined as a Gaussian. That's the very, very important property. So normal 1, normal 2 by normal 3 is a normal distribution again. So We'll see why, and then I'll give you some homework to compute the exact term. But anyways, so we'll see. This is, we know this as, we have defined this already by the forward process, alpha t xt minus 1, 1 minus alpha t. The identity matrix xt minus 1, alpha t minus 1 bar x0, 1 minus alpha t minus 1 bar identity, binormally distributed xt, alpha t bar x0, and 1 minus alpha t bar identity. Okay, so now if I have this terms over here, I will have a list of, we know that we will have a list of exponents, right? Exponents and a leading terms. So let us try to write this down. Look at this. So what is this going to be? So it is going to be 1 by 2 pi to the power d by 2, right? And this is identity matrix. The identity matrix, the determinant of an identity matrix, you can just take is 1, right? And then we could have the covariance being taken out. So we know that it is sigma to the power half for a covariance, for an identity matrix is 1 minus alpha t. So for, I'm doing it for the 1 only, and the 3s we can just follow, but rest of them we can just follow, right? Into the determinant of I, which is equal to 1. This is 1, right? So what I'll get is, I will get 1 minus alpha t to the power half, right? I will get another term 1 by 2 pi to the power d by 2. That is the dimension of the latents or the image dimension. One thing to note here is the encoding does not bottleneck in a diffusion model. That the input dimension and the latent dimension is the fixed, is same for a diffusion model. That is a, because you're just adding noise, the dimensionality should remain the same. So again, the variance will be added, multiplied alpha t minus 1 to the power half. And I will have a denominator term 1 by 2 pi to the power d by 2, right? And I will have the variance to be 1 minus alpha t bar to the power half. And I'll have a list of exponents, right? I will have these exponents to be very good. I will have them to be, we know that this is half xt minus root alpha t squared by 1 minus alpha t minus half into xt minus 1 alpha t minus 1. Just writing x minus mu by sigma. That's all I'm writing. x0 squared by 1 minus alpha t minus 1. And I will have whatever is in the denominator as 1 minus alpha t bar xt minus root alpha t x0 squared. Right? This is what I'll have in the exponent. Here, this will help me to do a particular computation. You can see this. You can write this as 1 by 2 pi to the power d by 2 into the square root of, right, into the square root of 1 minus alpha t, 1 minus alpha t minus 1 bar, and 1 minus alpha t bar. And I will have a list of the exponents where I will have this. If you write down this sum of squares, complete the squares, I will have this as x minus some mu q of xt comma x0, because that's what, complete the squares and write this in terms of xt minus 1. So you see there's xt minus 1, there's x0, and there's xt. I will write this as xt minus 1. I will put everything else to qt and x0. So I'll get this as this by the same term, 1 minus alpha t 1 minus alpha t bar 1 minus alpha t minus 1. Right? So this is what I'll get. So I will get the terms as this. So now I exactly know this is a normal, is it again, the product divided by a normal distribution is a normally distributed random variable again. So your homework is complete the squares and show mu q of, please post it on the channel, just algebra at the end of the day. This is equal to alpha t root alpha t 1 minus alpha t bar xt by 1 minus alpha t bar plus alpha t minus 1 root over and 1 minus alpha t x0. This is what you have to show. The variance we have already shown. So now if you ask me what is q of xt given, or xt minus 1 given xt given 1 x0, this is normally distributed as, with xt minus 1 as the random variable, alpha t 1 minus alpha t minus 1 xt 1 minus alpha t bar. Okay, this is what we define this as, and 1 minus alpha t 1 minus alpha t minus 1 bar by 1 minus alpha t. So this, you can look at Bishop as well. Bishop also has this factorization, the product but divided by a normal distribution. Product of normal by a normal distribution is a normal distribution. You can look at it for help. This is just algebra, therefore we're not going to do that. But anyways, so this term that I have over here is normally distributed. So I can fairly assume, what I'll assume the model to be, model assumption is, for simplicity, xt minus 1 to be xt to be normally distributed as xt mu theta of xt comma x0 and sigma q squared ti. And I'm not going to learn this. I'll be equating this equally. So I will say that for this q process, which is the variational process, I'll say only learn the means. Learn the mean. Variance remains same. Variance fixed to variational process. So once you do that, we know that the KL divergence between two normal distributions are, yes, very good. This is normal 1, mu 1, sigma 1. We have derived this in class, mu 2, sigma 2 to be equal to half times log of sigma y or sigma 2 by sigma 1 minus d plus trace into sigma 2 inverse sigma 1 plus mu 2 minus mu 1 sigma 2 inverse and mu1 mu2 minus mu1, right? So you can clearly see, equating sigma 1 to be equal to sigma 2, if I equate these two, then this goes to 0. These two go to 0 because sigma 2 inverse is equal to sigma 1 inverse, and minus d plus d goes to 0 again. And this last term, if it's a diagonal matrix, becomes just half, again, sigma q squared t, because this is inverse. This is the diagonal matrix. If it's a diagonal matrix, it just becomes the covariance or the variance structures of the matrix into mu q. And it's a constant diagonal matrix. It's not even a diagonal elements are different. So this is mu 2 minus mu 1 squared. That's all it is. So this becomes an MAC loss. MAC loss, right? So between the means. So if variances are fixed, are same, and fixed and a scale and a common scaling of of the identity matrix, then loss is just an MSE loss, the mean square error loss, right? So we have mu2 minus mu1 is what will be the, or mu q minus mu theta. So if you can write down the KL divergence between q and p theta, so our KL divergence dKL q and p theta is nothing but 1 by 2 sigma q squared t, which is a constant again. This is at time t. Let's assume at time t is mu theta xt comma x0 minus mu q xt comma x0. This is my MSE loss. So I will learn this, and this is known. So let us look at it. How is it known? So what we have derived till now, we have derived the joint distribution of the posterior of the variational distribution. We have seen what the parameters are learning. They're trying to closely track the posterior of the variational distribution. We have seen how the expression of the ELBO factors out. And now, finally, what I'll do is I'll try to derive how this is going to be implemented in practice. So we showed that it is a MSE loss, but what are we going to do the MSE loss between? So you could say, okay, I can be able to learn this mean directly, but I can directly learn this mean and then do my computation. That is quite a valid way. So I could say I learn a model, that is option 1, learn a model tracking mu q of xt comma x0 equal to, again I'm writing for you to remember, alpha t minus 1 xt plus alpha t minus 1 bar 1 minus alpha t x0. Okay, I can do that, track this. I can put this value in the equation and I can track the data. But for this, I need both xt and x0. It's a bit of a cumbersome process. I will have to do the forward process and things like that. So what I'll do is I'll do a reparameterization trick. Reparameterization. So reparameterization is what I'll do. How will I do the reparameterization? Remember that we had shown the forward process gives xt is equal to root alpha t x0 plus 1 minus alpha t epsilon, isn't it? So now I will say that I can write x0 as, I want to write this as a single random variable, and I'll show you why that helps. X0 as, I just want to write in terms of xt and some noise, which will help me a bit. So x0 as 1 by root alpha t. From here, I'm just going to rewrite this equation as minus 1 minus alpha t bar epsilon. This is what I'm going to do. And I'll put this value in this equation, right? If I put this value in the equation, what will I get? I'll get xt comma x0 as alpha t 1 minus alpha t bar xt plus root alpha t minus 1 bar 1 minus alpha t bar xt minus 1 minus alpha t bar by alpha t bar epsilon. I whole divided by 1 minus alpha t bar. So as soon as I do that, the numerator becomes alpha t 1 minus alpha t minus 1 xt, and this term on the first hand is becoming 1 minus alpha t by root alpha t xt minus so this term that I have over here is going to remain, and I'll have this term becomes 1 minus alpha t bar root over alpha t into 1 minus alpha t epsilon, right? If you're not following what I did, I just wrote alpha t minus 1 by root alpha t to be 1 by alpha t. This is because alpha t is equal to the product of t equal to 1 to t, alpha t, which is equal to alpha t product of t equal to 1 to t minus 1 alpha t, right? Very nice. Which is equal to alpha t minus 1 bar. So if you divide this, you'll just get 1 by alpha t. Very nice. And then I get 1 minus alpha t bar. So if I take xt common over here, so what will I get? I'll get alpha t 1 minus alpha t minus 1 bar alpha xt plus 1 minus alpha t. I have 1 by root alpha t here xt. This is what I'll have, right? And I'll have this divided by 1 minus alpha t bar, and I'll have a term, a negative term, where I'll have 1 by root over of alpha t 1 minus alpha t bar, right? Into 1 minus alpha t, right? Okay, it's charging. So 1 minus alpha t into epsilon, right? This is what I'll have. No doubts? Okay, so this term comes here and this term goes over here. So I will have this terms being cancelled, and I will have alpha t minus 1 bar into alpha t and 1 minus that. So that is 1 minus root alpha. This is 1 minus alpha t bar. So this will be 1 by alpha t xt minus 1 minus alpha t root alpha t 1 minus alpha t bar. This is my mu q xt comma x0. And this becomes xt comma x, just t, right? Just the tth value. And I have a noise term that is added from normal 0, 1. This is from normal 0, 1. Right? So now I can say mu theta of xt, this is my reparameterization. Reparameterization is just linearly shifted as follows: 1 by alpha t xt minus 1 minus alpha t. So I can always learn a linearly scaled function, alpha t bar epsilon theta xt comma t. So now you can see if I make the subtraction of these two terms, mu theta xt comma t minus mu q xt comma t squared, you get 1 minus alpha t squared alpha t 1 minus alpha t bar. This is the common term, and I'll have epsilon theta minus epsilon xt. This is why it's called a denoising term. See, so this is my loss function, right? So you can clearly see that this is equal to, so if you are trying to understand what does this mean in terms of the architecture, it means that, so this is 1 by 2 sigma qt squared. So if I just write this as 1 by 2 sigma qt squared, these are all constant terms, and you may just forget about them, is what the paper tells, because often these constant terms really do not make a difference, because what you get as a loss function now, loss of the loss function is just this. This is a summation over t equal to 2 to capital T, the expected value of q of x1 given x0 log p theta of x0 given x1 minus dkl, the expected value over xt given x0, or this is just the expected value of xt given x0, a list of constant. Let's put this as ct, which can be computed because all of these terms are fixed from beforehand. Ct into epsilon theta x theta t minus epsilon. So this is what you get. Or let us put it as kappa kt, some constant kt, right? So what I get is it can be shown empirically that since there are infinite steps, right? X0, x1, dot, 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 xt, the last step, which is this, the last step need not be separated, right? Because you will see in the denoising, as I've shown over here, as I've shown over here in the denoising, the denoising happens automatically even at the second stage. Even when you have reached the second stage, the denoising has actually happened. So the last step really doesn't count. So the last step need not have, you can learn a separate encoder or a decoder for it, but we do not really need to learn a separate decoder, is what the authors say. So what we can clearly do is we can learn a common encoder for across all time points. So what you can do is you can have the loss function say the expected value. So you can say you sample x from the data, right? Next, what you do is you sample a t from uniformly between 0, 1, dot, dot, dot till t, or rather 1 to capital T. Because this is a summation again, each of them have equal terms. Instead of doing for one data point, all the terms, you can do it for, if you just divide this entire equation by 1 by t, this becomes an expectation over the uniform distribution of t. So it's like you sample a data point, you sample a corresponding t for the data point, that is the time point in which you want to get for the tth noisy version. Okay, and then what you do, you sample q of xt given x0, because we know the distribution again. And once you do that, you can do kt epsilon theta xt comma t minus epsilon squared. You can do this. So this is just training a MSE loss. So you club t equal to 1 and t equal to 2 to infinity as one step is negligible over large number of steps. Okay, so now it is, what does it mean? If you, this is now, once you have this, is just an MSE loss. MSE loss predicting the noise added to get tth noisy version of the data. Okay, so let us write this down as, how will you write this down? So this will become, the model will be, so remember again, the noise, if you have to add a noise, the noise has to have same dimension. So I can just take the data in. This is called a U-net. You can use a U-net or a transformer. We'll see transformers in details, but U-net first compresses the data and then increases it. You can see the U-net architecture. This is an encoder decoder architecture without a variational part of it. So xt, it'll get you back the epsilon. You give the tth noisy version. See, this depends on the tth noisy version. And you give an embedding vector. Embedding. So what do I mean? So say the encoder gives you a encoding of the data, you add a time point embedding. It could be sinusoidal embedding. You can look at it. Time embedding. We'll see it in coding. This say you could be a sinusoidal embedding and so on. So you could have, this is from the data. This is epsilon of xt comma xt, and you can add the time embedding. So once you do that, the model will be able to predict the noise. So the same model for each of the time points will be able to predict what was the noise that was added. So at every time point, it will be able to predict. So if you put t equal to 2, t equal to 3, it will be predicting what was the noise that was added, right? So now you train this model to predict this noise, and then now during inference, what will I do? So you remember p theta of xt minus 1 given xt is distributed as normal xt minus 1 given mu theta of xt comma t and sigma square q, right? This is what you define this as. So therefore inference, that is denoising from getting novel data can be done in this form, where you can write xt minus 1 as mu of xt comma t plus sigma square t into epsilon, where it is distributed as normal 0, 1. As we have already shown that any normal distribution can be written as mu plus sigma z, where z is epsilon here because of the notation that we are following. So now this term over here, we can clearly write this as, from this equation, we have already written this down. Just copy this. Okay. Okay. So this is already known to us. And therefore I can write this as 1 by root alpha t xt minus 1 minus alpha t root over of xt 1 minus alpha t bar. And I can write epsilon theta of xt comma t plus sigma q square t. So this is like you take the tth noisy version xt, pass it through the decoder, which is the unit. It gives you the noise corresponding to it. You then remove the noise, and get xt minus 1. So and even during inference, in DDPM, you keep adding noise. This is to determine, this is for stochasticity. That is even from same latents, you can get slightly different outputs, right? So this is all about denoising the diffusion model and so on. So once you're able to denoise the diffusion model, or you take xt and over time you sample from normal 0, 1 distribution and you pass it through the unit, it will give you the noise that was added. You remove that noise and take a gradient and take a stochastic step for introducing variability in the data. It's how you implement it, but it comes directly from this equation that we have defined from the decoder, right? So this is denoise. You can define this is denoise, and this is variability or novelty. So you can look at the, please try and derive the entire thing once. And if you have any doubts, please feel free to ask in the group. And also we'll, during the doubt clearing session, please be clear about what the doubts are, because we've done everything in detail. And I've given you a homework on how to get the exact formulation of this, where is it? The mean of the variational distribution, posterior of the mean variational distribution. We found the variance. So we have been able to do inference. We have been able to get the loss function, which is again just minimizing the root mean square error or mean square error of the data and the noise. The model is actually predicting what was the noise that was added and removing it at every step during inference, right? So with that, we come to the end of denoising diffusion model, probabilistic model, DDPMs. We'll be seeing score-based diffusion models in the next class, and we'll be going into energy-based models, which is another variation inference model. And we'll be able to, that will give us sort of a closure on understanding variational inference. And you'll be able to have a bigger picture. So we already now know what is the EM algorithm, how we can remove latent variables. We have been very, very familiar with the ELBO term. And we have seen that even in diffusion models, which has a non-learnable forward process, to have this the same ELBO, which only becomes equivalent to learning the denoising step in the reverse process. So that's what the diffusion models are. And please feel free to post your questions in the channel, and we'll catch up in the next lecture. Thank you. Stop recording.